Welcome to BVS Pragati channel. In this session, let's have a look at frequency modulation. So in frequency modulation, the frequency of the carrier is varied in accordance with the instantaneous value of the modulating signal. So how is it varied? Let's have a look at it. So if you see here, the mathematical expression says that F is equal to Fc into 1 plus K Vm cos omega mt. So this is the Vm cos omega mt is the modulating signal. So we see that this is what is the frequency of the frequency modulated wave. K is the proportionality constant, Fc is the unmodulated carrier frequency. So what is the maximum deviation? When will the maximum deviation occur? When cos omega mt is equal to plus minus 1. So F is equal to Fc into 1 plus minus kVm. So this kVm is what? Is the amount of frequency deviation that we see. So delta is equal to kVm into Fc. That is the maximum deviation that we would see. Instantaneous value of FM voltage. So what is the value? V is equal to A into sine omega Ct plus delta by Fm. This delta is what is the frequency deviation by Fm into sine omega mt. So MF is equal to frequency deviation by modulating frequency, which is equal to delta by Fm. So this is how a frequency modulated signal appears. So here is a variation in the modulating signal, and accordingly we see that the frequency is, so you see that the frequency is varying, okay? And the amplitude remains a constant. So the amplitude of a frequency modulated wave before and after modulation is the same. So now let's discuss in detail frequency modulation. So we have seen the carrier frequency is varied in accordance with the instantaneous value of modulating signal. Frequency deviation depends on modulating voltage, and Fd is equal to Em by 2 pi. Fd is also equal to Fc minus Fc min or Fc max minus Fc. Depth of modulation index in Fm is defined by Fd by Fd max. Now, modulation index depends on the modulating voltage and modulating frequency. Mf is equal to delta by Fm. And delta is Em by 2 pi if you see over there also. So Em by 2 pi. So Em by 2 pi Fm. That is what is MF. So the maximum permissible MF is 2500. Unmodulated carrier power is equal to modulated carrier power. That is what we have seen. After modulation, the carrier amplitude decreases with modulation index. Sometimes the carrier amplitude becomes 0 for some value of MF. So if that happens, that value of MF, that is modulation index, where the carrier amplitude becomes 0 is called eigenvalue. The main advantage of FM over AM is high S by N ratio. Why? Mostly the signal is contained in the frequency and not in the amplitude variation. So normally there is less noise in frequency range where FM transmission is done. The other advantage of FM is we have seen that before and after modulation, the power remains the same. Let's discuss some more details. So what is the disadvantage of FM over AM? More bandwidth is required and the receiver becomes costly. The frequency allocated for FM is 88 MHz to 108 MHz. Since this is the frequency range and this is where space wave propagation has to be employed, it is transmitted to limited distance. Since it is transmitted to limited distance, other areas can also use the same frequency. So same frequency can be allocated to other regions also. So we have seen E is equal to EC sin omega Ct plus MF sin omega mt. This is the frequency modulated signal, the voltage of frequency modulated signal. Propagation range is 30 MHz to 300 MHz. Frequency allocated is 88 MHz to 108 MHz. The bandwidth is 200 kHz. IF is 10.8 MHz. FM is 15 kHz. Telephone modulating signal is between 300 Hz to 3.3 kHz. Fidelity is good because maximum modulating frequency allocated in FM is 15 kHz. Narrowband FM. So when bandwidth is twice FM, that is when the modulation index is less than 0.5, you call it narrowband FM, and in that case bandwidth is twice FM. And if MF is greater than 0.5, bandwidth is twice FM plus FD. In that case, bandwidth is equal to twice FM into 1 plus MF. In that case, it is called broadband FM. So this is how you indirectly generate FM. What you do, you have a modulating signal, okay, integrate that, you get EM by omega m cos omega mt, and here using EC sin omega ct, this signal will undergo phase modulation using this. So EC sin omega ct plus EM by omega cos omega mt. So you get a frequency modulated signal. So let's discuss about various types of modulators. So indirect method of generating FM is called Armstrong method of FM generation, and crystal oscillators are normally used. Direct method of generating FM requires automatic frequency control circuits because crystal oscillators cannot be used. Noise in FM. Noise in FM, noise is essentially contained in amplitude. FM signal has a constant carrier amplitude. Because of this, FM receivers contain limiter circuits that restrict the amplitude of receiver signal. Any amplitude variation occurring on the FM signal are effectively clipped off so that the information is not lost. So because of this clipping action, noise is completely eliminated in FM. Now let's understand one more concept called interference or capture concept, which we normally see in case of FM signal. A major benefit of FM is that the interfering signal on the same frequency will be rejected. If the signal of one is more than twice the amplitude of the other, the stronger signal will capture the channel and will totally eliminate the weaker interfering signal. This is known as the capture effect in FM. In FM, the capture effect allows the stronger signal to dominate while the weaker signal is completely eliminated. However, when the strength of two FM signals begin to be nearly the same, the capture effect may cause the signal to alternate in their dominion of frequency. So sometimes one signal might dominate, sometimes the other signal might dominate. Despite the fact that FM has superior noise rejection qualities, noise still interferes with FM signal. This is particularly true for high frequency components in the modulating signal. Okay. So since noise is primarily sharp spikes of energy, it contains a considerable number of harmonics and other high frequency components. These high frequency components at times will be larger in amplitude than the high frequency content of modulating signal. This causes a form of frequency distortion that makes the signal unintelligible. So to overcome this problem, most FM systems use a technique known as pre-emphasis circuit in transmitter and de-emphasis circuit in the receiver. Let's have a look at what pre-emphasis circuit means. So in pre-emphasis circuit, at the transmitter, you are using a pre-emphasis circuit. This pre-emphasis circuit is normally a high-pass filter. And what does it do? It amplifies the high-frequency component more than the low-frequency component of the modulating signal. The pre-emphasis circuit increases the energy of higher content of high-frequency signal so that it becomes stronger than the high-frequency noise component. So this improves S by N ratio. So this is normally used before modulation and in FM transmitter. So it is usually since it's a high pass filter, it is usually a differentiator. If this is a differentiator, the de-emphasis circuit should be used after demodulation, and that should be a low pass filter. So that means that it should be a integrating circuit. Okay, so what we have seen, in this session what we have seen how in frequency modulation the frequency of the carrier is getting varied with respect to the instantaneous value of the modulating signal, and we have understood what frequency deviation means, how it is related to the voltage of the modulating signal, and we have understood what modulation index means, and also we have understood about the various propagation ranges. Okay, so we have seen that the frequency allocated for FM is 88 megahertz to 108 megahertz. So in the next session, what we'll see is we'll have a look at de-emphasis circuits, and also we will look at the phase modulation aspects of the communication system. That's all for this session. More in the next session. Thank you. Thanks a lot and I wish you all the best.